All right, this one is number 19 from the review of Unit 2. So this says a sprinter starts from rest at the start of a 100-meter race and accelerates at 2 meters per second squared for 25 meters. Having reached his maximum velocity, he runs at a constant velocity for the remaining 75 meters of the race. As he crosses the finish line to slow down, he slows himself down with a constant acceleration, stopping 20 meters beyond the finish line. A, how long did the 100-meter race take? What was this runner's acceleration, magnitude, and direction for the 20 meters after the race? And what was the sprinter's average velocity for the entire 120 meters? All right, so this is broken into stages because we have an acceleration from one stage. So we have an acceleration problem. Then we have a section of, that's a constant velocity. And then we have another acceleration section, but it's a negative acceleration. And it tells us how long each of these sections are in meters, not time, but distance, displacement. All right, so we have 3 stages. We know this one is 25 meters. We know this one is 75 meters. And we know this stage is 20 meters. All right, so we're going to look at that first stage first because we want to see how long it took for the 100 meters. So let's break this down. We know that this acceleration over this distance would take a certain amount of time. So let's say our acceleration for this part is 2 meters per second squared. Our distance for that first part of the acceleration is 25 meters. Let's call this x1. And we know we start from rest, 0 meters per second. All right, so the first thing we need to solve is how fast he was going, because that'll be handy for the second part, because we don't know how fast he's going, but we can solve for it. All right, so we're going to use VF equals, I'm just going to throw in the algebra, hopefully you can see where it came from, 2a delta x. Came from equation number 4, V naught drops out. All right, we throw in the numbers. I'm going to get a little bit sloppy here because we're going to run around a room if I don't. And this is 2 meters per second squared, all times, extend them, 25 meters. All right, we throw that in and we get 10 meters per second. So that's his top speed. That's how fast he's going to be going for this section here. And that's how fast he got when he got to this 25 meters. So it asks how long the 100 meters take. So we need to find the time for this accelerated motion and we need to find the time for the constant velocity. So that requires 2 equations. 2 to 0 to 25 is, we're going to use equation number 1, VF minus V naught divided by A. So we get 10 meters per second divided by 2 meters per second. So our time of that first interval is 5 seconds. So this is t equals 5 seconds. All right, so we're not quite done. We got to find the time for this second stage. Well, that second stage is just a constant velocity. So our V equals delta x over t holds true. So our t, I'm going to scroll that out, I don't like it. T from 25 to 100 is just delta x divided by v. Our delta x is 75 meters. And our velocity we found was 10 meters per second. So that gives us the second leg is 7.5 seconds. There we go. All right, So the time for the 100 meters is 5 plus 7.5, so 12.5 seconds. Alright, so that's part A. That was everything we had to do for part A. So what was the runner's acceleration for the 20 meters after the race? So now we're looking after the race. We're finding A, meters per second squared. And we know its initial velocity. So we're coming in and we're slowing down. So initial velocity is 10 meters per second. And we're coming to a stop, 0 meters per second. And we want to, and we know it takes place over 20 meters, x. So we don't have time. We need to solve number 4 for A. So A is Vf squared minus V naught squared divided by